Is that okay with you?
Well, I guess we can get started. What do you think, huh?
Yeah.
Okay. Well, and welcome everyone for being here. I'm Don Nab. I'm the chair of Mideast Region Astronomical League, and big thanks to Sue Ann for doing this, and also to Howard Dew. He's the one that floated the idea of having this as our first ever, I think, event that we had all of MERAL invited to. So thank you so much. So just I have one slide and what I'm going to show. This is, of course, the Green Bank Telescope that Sue Ann is going to talk about. And Sue Ann, I hope you'll tell us a little bit about yourself too. But for those who were on the very start, I have to tell one story. This is a picture I took from the 2019 StarQuest, and it's amazing to tour this telescope. I got as high as here. The day, probably the elevator, the day before, other people got as high as here. I know Howard was all the way up here. The one story that was told, I think the observatory director told the story that when they paint this thing, of course, they hire people to come in to paint, and he asked them, where they get used to it. And they told him, yes, you get used to it. He said, you mean the height? He said, no, you get used to being terrified all day. So one thing I want to show you is, if I can find it here. Oops, 1 second. Where'd it go? I'm going to show you StarQuest. 1 second, it dropped off my screen here, but I'll be right back. Here we go. So I just want to show you this. Everyone's seeing the Green Bank StarQuest screen?
Yeah.
We appreciate you advertising us.
It's an amazing event. I was there for the first time. My wife and I and some other folks from our club in 2019. And I sure hope we have it this year, because this was the most amazing experience of our life. Everyone was so welcoming. The camaraderie is excellent. The presentations, every night there's a presentation. There is a wonderful raffle where you can pick up all kinds of equipment and astronomy doodads. If you like camping, it's a great place to camp. You're inside the dish the whole entire time. If you don't like a camp, there is a bunkhouse. There is a place to get something to eat. The only place I've ever seen a microwave oven inside a Faraday cage. So I just want to give a quick plug for it. If you want to have an experience you'll never forget, and assuming it's held this year, come to StarQuest. So with that, Ian, I'll turn it over to you.
Thanks. That was great. Thank you for doing that. And I see a lot of StarQuest people on tonight, and so I know they appreciate it too. So if you guys will mute your microphones. So Mike, that would be you, and Dave, anybody that I don't see the little microphone with the slash across it, feel free to unmute at any time if you want to shout out a question. And you can also put questions in the chat. But my name is Sue Ann, and if you do come to StarQuest, you'll see me there. If we have StarQuest, I will be in amongst and helping to give you some tours and show you how to use some radio telescopes. So it's a cool star party because it's optical and radio astronomy combined, and we think it's pretty unique across the whole country. So we'd love to have you come visit. I am an educator. I'm a science teacher by training. And, I started out actually waiting tables, and then I figured out I'd go back to school and get my master's degree in science education. And I never regretted it for a second. I enjoyed teaching in the classroom. And then way back in 1989, I got a chance to come work at this fabulous federally funded research center in the middle of nowhere in West Virginia. And it was home. And I've been there ever since. And I operate educational programs. Hi, Stephen, could you mute yourself, please? And I operate educational programs and write grants to do cool educational things to give people that the sense of what it's like to be a scientist. And that means you don't know the answer ahead of time, and you have to collect data and use your mind and build up evidence to see what you can learn about the universe. And so I got to do that using a very ancient little telescope called the 40-foot, and I make everybody use it that comes to visit. And then in later years, we got a robotic telescope online for educational purposes, and I hope to show you how to use that at the end of the presentation. So, like I said, type questions in the chat, unmute and ask questions at any time. Dawn's going to help keep track of things for me. I'm going to share my screen in just a minute. But I would love to know what your questions are, and I'll make sure I try to touch on those things before we conclude. But what I'm planning on doing right now is giving you a tour of the observatory as if you were visiting. And you're going to see the telescopes, and you're going to learn a little bit about the radio universe as well as we go along. So let me share my screen, and then I'll find my PowerPoint presentation. Okay. So, and I think that might be it. Nope, I don't want to give you the one for kids. Let's see here.
Seeing the Skynet right now, we're seeing.
Yeah, that's what you're seeing right now. Let me close this one.
Here we go. I see your PowerPoint now. Yep.
Yeah, cool. There it is. Good.
Yep.
All right. Okay, so here we go. You've already seen one picture of the Green Bank telescope. Its full name is Robert C. Byrd Green Bank Telescope, and we can talk about that later if you want. But it was constructed and completed in the year 2000, and it sits in a valley in the vicinity of Green Bank, West Virginia. And I love this particular picture of the GBT, as we call it, because what you can see behind it is very important to us. So take a look at the view behind the GBT as you're looking at this big telescope. And you should notice lots of beautiful mountains. And I hope that you also notice that there are no houses or farms or any sort of human development back behind the telescope. That's all national forest, and really, really important to being able to do our science. We'll talk about that a little bit more as we go along. So the Green Bank Observatory has been in existence since the late 1950s. And it is funded in part by the National Science Foundation. And our job at the observatory, not me, I use the royal we, but our job at the observatory is to make sure that astronomers in our country, and around the world for that matter, have state-of-the-art radio telescopes to use to do their science. So it was decided way back in the 50s that it wasn't cost effective for individual universities to build their own radio telescopes, and instead they built a national facility and allow everybody to use it. And people use the Green Bank telescope to do their own science free of charge. So here's a view of the GBT in action. This is a time-lapse series of photographs. It's pretty old, but it shows you the way the telescope moves over the course of a day. Sometimes it wiggles back and forth, and sometimes it very smoothly moves through the sky. So as optical astronomers, I imagine that most of the time you are doing the latter. You're making a smooth motion in the sky with your telescope to stay pointed to the object of interest. But with a radio telescope, if you want to make a picture of something, especially one dish like this, if you want to make a picture of an object in the sky or an area of sky, you got to do this little wiggly motion that you see right there. So the whole telescope itself has to wiggle back and forth and capture the electromagnetic energy from different parts of the sky by moving it, the entire structure. So when you see it wiggling, it's probably making a map, as we call it, or creating an image of an area of the sky. So it was completed, as I said, in 2000. It is quite large and it's quite versatile. And one of the reasons why this is such a versatile telescope is because there's just one dish. So just like with your optical telescope, you can put different lenses in and different filters in. And it's like you have a whole new instrument in terms of observing. We build different receivers to put at the focal point. And it's like we have a whole new instrument every time we build a new receiver with a different capability. So it's used by lots of astronomers to do all kinds of different sorts of science. And we'll talk about it in a little bit. So this is a cartoon of an optical telescope, and let's hope it's an Orion telescope and not something somebody picked up at Walmart. But I just wanted to bring home the fact to you that optical astronomy, you're collecting light, and you all are probably using CCDs at the focal point in order to capture that light and digitize it and turn it into images. And we do the same thing with a radio telescope. Only a lot of people seem to think of radio astronomy more as this sort of a thing. So this is a direct TV satellite dish cartoon, but that dish is a mirror, and that dish reflects radio waves just like many optical telescopes work if you have a reflecting telescope. So we're picking up radio signals, you're picking up light waves, but it's all the same kind of thing. Now, one other advantage that both you as optical astronomers and we as radio astronomers have to our advantage is that our instruments can be built on the ground. And with modern technology, you can compensate with optical telescopes for a lot of distortions that might happen through the atmosphere. And with radio telescopes, the radio waves are so long in wavelength that the atmosphere does not really distort the signals very much at all. And so both types of telescopes can be built on the ground, and that is a huge advantage for studying this part of the electromagnetic spectrum, because we can upgrade and innovate and work on the same telescope for a long time. And so radio telescopes and ground-based optical telescopes last a long time. There are many still in use 50 or 60 or more years after they were originally built. So the Green Bank Observatory site, sort of an aerial view, kind of looks, it does look like this. This is it. And so in the foreground, you can see a telescope. That's a radio telescope. And behind it is our science center. And this is where a lot of the happenings at StarQuest happen until it gets dark and you go observe the sky with your telescopes. And then we have a lab area where a lot of people work. And a mile and a half down the valley sits the Green Bank Telescope. So it's a mile and a half away from where most of us work. And that is also on purpose in order to minimize the radio pollution that we are generating, from reaching the telescope. And over here in the far right, you can also see two other little dishes there. One of them is pointing in a direction and the other one's kind of pointing straight up. So this is a view of the site, sort of as you come right in, and you're going to see what you can see moving deeper in toward the mountains as you go. So I thought we'd talk a little bit about a couple of the historic telescopes that are on the property. And if you look at the bottom image here, this is what you'll see if you come visit Green Bank. And it's not a telescope. I mean, it doesn't have a reflector. It's not really a dish. And so it's not a telescope per se, but it is an antenna. And this view of it shows you the parts of the antenna that actually do the work. And that are these horizontal metal bars that go across. This is a replica of an antenna that a fellow called Carl Jansky built in the late 1920s. And he was working for Bell Labs, and his job was to determine the feasibility of shortwave radio as a future telephone system. So, it was kind of like really a good predictor of the future. So they were trying to see if they could do build a wireless telephone system using shortwave. And shortwaves are really actually very long waves. But Carl Jansky built this antenna, and his job was to determine what might cause a problem with that. And as you all know, thunderstorms do create a lot of static on your AM radio. If you're driving down the road and you're in the middle of a thunderstorm, you can hear lots of static when lightning strikes. And so he knew thunderstorms would be a problem, but he was looking for other sources of man-made or natural-made radio signals that might make it not feasible to have a shortwave telephone system. And he did the experiment for over a year. And one little thing happened that would have escaped the notice of many people. And that is that there was a little signal in his data, not big enough to bother Bell Labs with, but this little signal had a sidereal rate. That is, it rose and set with the stars. It didn't follow a solar cycle. It rose and set with actually the center of our galaxy, the galactic nucleus. And he was intrigued by it and watched it for a whole year and tracked it as the year went by, and was able to definitively say that radio waves were being produced. Could I get somebody to mute for me? That radio waves were being produced by something in the center of our Milky Way. And that marked the discovery, the first discovery of cosmic radio waves, and the dawn of radio astronomy. And this was in 1933 when the article that he wrote about appeared in the front page of the New York Times. It was 1933. So that's when radio astronomy started. This red, white, and blue telescope is a follow-up instrument to Jansky's discovery. Bell Labs said, that's nice, now get back to work. And so Carl Jansky really couldn't follow up on his discovery. And a fellow called Grote Reber did. And he built this dish in his mother's backyard outside of Chicago, Illinois. And used to make first maps of the radio sky. I'm going to show you some of his data in just a second. So do we have a mute problem with somebody? If so, if you click that mute button, it'd be awesome.
I just,
you want to ask a question?
I'm tracking him to try to mute. I'm muting
Okay.
my CM, Sue.
As you go. Okay, cool. Thank you so much. And this is what Grote Reber looks like. This was sort of his graduation picture from high school, and I just think he's adorable. So I wanted to show you what Grote Reber looked like. So he built this telescope in his mom's backyard with his own hands, with his own material, because he was curious, and he was also a ham. And I don't know if any of you have that as a hobby as well, but amateur radio was something he had done and excelled at, and he wanted to push it to the next level. And so he followed up on Jansky's experiment and detected new radio objects in the sky. And this is him just a little bit later in life. He disassembled his telescope and rebuilt it in Greenbank, West Virginia. So you can pat it, you can see it now, you can stand by it and get your picture with it now. And it is actually the telescope that he originally built in the 1930s, as I said, in his mom's backyard. And this is what his data looked like. So he really graduated to the big leagues when he got a chart recorder, because when he started, he was like watching a voltmeter and writing down numbers as the sky passed by. So what you see here is the sky passing by over time. And this was a strip chart recorder, and you see 4 strips of it. And all the spiky things that you see going up and down is what we call radio frequency interference. This is the equivalent of light pollution. It is the bane of radio astronomy. It is man-made sources of radio waves. And in this case, these were spikes from streetcars, because the streetcars are electrified and all those sparks flying were creating this radio frequency interference. But underneath those spikes, you can see some systematic humps in the data. And those are probably, just looking at it, are probably the passage of the Milky Way plane, the galactic plane passing by. So he did this for several years, really the only person in the world doing radio astronomy at all, just all by himself after work, in his basement. So I think he's pretty cool. So this interference that you see, all these spikes that you see, have gotten worse over time. We don't have streetcars near Green Bank, but I mean, radio frequency interference is a continuous problem, and a problem that gets worse as we go into a more of a wireless age and an intelligent, home that has all these Bluetooth and wireless devices in our refrigerators and everything else. So it was really important when they established the Green Bank Observatory that the government also established a zone around us, and that green box is the National Radio Quiet Zone. And the little black dot is where we're located. The bottom left edge of the box, of the green box, the bottom right edge, excuse me, goes right through the University of Virginia campus in Charlottesville, Virginia. This is a 13,000 square mile area that is slightly protected for radio astronomy. And by that, I mean that fixed commercial transmitters that have to get an FCC license, like cell phone towers, for example, fixed commercial transmitters built inside this box have to meet our limits for how much signal can reach our telescope. And so before you even build a tower of any kind inside of this 13,000 square mile box, you have to send your application to the Green Bank Observatory, and we'll do a terrain study to see, given the parameters of your tower and the frequency and the power that you're going to broadcast, how much signal will make it to the telescope. So we do a simulation there. And if you're good to go ahead and build. And if not, we've got some work to do to enable you to do what you want to do. So what that means is that if you do come to StarQuest or visit the observatory at any time, don't expect your cell phone to work. It won't, it'll work. You can turn it on and take a picture with it, but you won't get any reception at Green Bank and that's on purpose. That's to protect the telescope against radio frequency interference.
Hey, Sue, there's a quick question about satellite, the Starlinks. Were they going to affect Green Bank at all?
Sure, yeah. So the entire astronomical community is so worried about this new constellation of satellites up there. And so luckily, at least in this case, they are working not only with the optical astronomy community, but also the radio astronomy community to try to mitigate that. They're going to be transmitting to Earth. There's no escaping that. And so those frequencies that they transmit at are going to be unavailable essentially for astronomy. So I think it'll even be worse for radio astronomy than the trails, left behind in people's optical images, because I guess you can use some software to get rid of those. And what we'll do is notch those frequencies out and just not observe the universe at those frequencies. That's what we do with the GPS satellites now. So this is, if you're taking a tour with us and you've seen the historic telescopes and we're moving on down through the site, this is one of our favorite telescopes, and it's 85 feet in diameter. And so we call it an 85-foot telescope. So the dish is 85 feet in diameter. And this telescope is called 85-1 because we have two others. This is our oldest telescope on the site. It was built here in the very late 1950s. And the reason why we love it is because the first modern search for extraterrestrial intelligence was conducted using this telescope by Frank Drake. And in fact, after Frank Drake used this telescope to look at two sun-like stars, two solar-type stars, to see if they had civilizations orbiting around them that were transmitting radio signals, and came up with nothing. He didn't find anything. But after he did his experiment, He convened a group of really smart people in all kinds of different science, including Carl Sagan, and they had a meeting here in Green Bank, and Frank Drake came up with an agenda, topics to talk about, and that agenda is now known as the Drake equation. So if you've ever seen the Drake equation, that was the agenda for a meeting that was held to discuss the probability of life in our galaxy, civilization, technological life in our galaxy. And so all that happened in Green Bank. If you come to visit, you can go sit in the lounge where they had a lot of their drinking components of their meetings, and you'll see the Drake equation right there inside the lounge. So that's what this telescope started out doing, although it also did cool things like measure the temperature of Venus. And later in its life, it looked at X-ray binaries in conjunction with another radio telescope on the site. So it was used for a variety of things for a while, and it's no longer in use now because, well, we just have bigger, better equipment to use now. So it's not in operation. But this is what it looked like inside the control room at the time that Frank Drake was conducting the first search for extraterrestrial intelligence. And that's a telescope operator right there. And you can still see part of that equipment in the control room today. This is the telescope that you might be interested in using. It's a 20-meter diameter telescope, and it was built on the site by the U.S. Naval Observatory. So the Navy, the U.S. Naval Observatory, is very interested in knowing the Earth's precise location in space. It's very interested in knowing how to precisely navigate by the stars. And so they're very interested in changes in the Earth's orientation in space, things that can be brought about by plate tectonic motions or wobbles in the Earth's axis. They want to know if they're using the stars or GPS to navigate, can that change by small changes in the Earth's orientation. And so they built this telescope and several others scattered across the country and used them to measure changes in the Earth's orientation in space by looking at quasars, very, very distant, very bright, point-like objects in space that emit radio waves. And they're so far away and so bright and so point-like that we expect their position to remain constant in the sky. And when the data collected by the telescopes indicates a change in that, we can infer that the change happened on Earth, and we can figure out what it was. And so this sort of geodetic measurement that was done with the 20 meters, that's why the 20 meter was built here. But they reduced the size of that program and essentially just abandoned the 20 meter to the site. And I got my hooks on it a few years ago with a grant to turn it back on for educational purposes. And it's a great telescope, actually, capable of doing, you know, some publication-worthy science. All right, so I'm going to show you a picture of the 140-foot in just a minute. But I should tell you that in 1955, when the NSF was determining to build an observatory for radio astronomy, they had already sketched out what they wanted to put there. And this was it. And if you look at this telescope, at this dish, and the way it's mounted, you will recognize that this is an equatorial telescope. It has an equatorial mount with the polar shaft pointing at the North Star. And a huge ball bearing, hydrostatic ball bearing here to keep everything fairly friction-free and tippable with relative ease. And so this model was built, this picture was made, plans were made, the 140-foot telescope before Green Bank was selected. And as they built this telescope, they realized that maybe they made a mistake and shouldn't have built an equatorial telescope at that time and should have gone with a different type of design, because one of the critical components was a bearing. This is a hemisphere that is perfect to within a couple of thousandths of an inch all the way around. And it sits at a very critical part of the telescope. So this was built and brought to Green Bank for the assembly of the 140 foot. And the 140 foot telescope took almost 10 years to complete, even though it was designed even before there was an observatory, because the equatorial mount really created some technological hurdles at the size that it is. So this is what it looks like today. So on the left, you see it at the very last stages of its construction before it had been painted. And then on the right, you see it more or less like it looks today. It's a little grimier than that today. Now, the 140 foot telescope was instrumental in advancing our understanding of astrochemistry. And so a lot of the first organic molecules discovered in space were discovered by this telescope, by astronomers using this telescope. And in its later years, it's been used to do such things as track a radio telescope that is in orbit that the Russians launched. It has been used to measure very small changes in the ionosphere of the Earth through a project that Haystack Observatory and the Air Force did together. And so it's still a pretty good telescope. It's a big telescope, it's a sensitive telescope, and it gets called into service quite a bit, but only for special projects that have funding attached to them. Because as you know, the Green Bank telescope exists now, and this one was officially retired when the GBT came online. And just a little quick note, because I can't give a telescope tour without showing you this one. This is my favorite telescope, 40 feet in diameter. It was built in 1962. And if you come to Green Bank, I guarantee you that you'll get a lesson on how to use this one. It has maintained its hands-on chart recorder, old school status, and it's absolutely delicious to operate and fun to learn with. And this was the telescope that I got to use as a teacher when I first came to Green Bank. And it rocked my world, changed my view of teaching completely, doing science with this little telescope. So I mentioned earlier that there was that we had an 85-foot telescope, and then we had two other ones. And this is a picture of all three of them together. So the one in the back is a picture of the telescope that Frank Drake used to conduct his SETI search. And then later on, we added these two other ones. And you'll notice that they're all pointed in the same direction. And that is because they were used together to simulate a much larger telescope. So unfortunately, in radio astronomy, if you want to see details, if you want to get a high resolution image, then you have to build a telescope that's bigger than any one single dish could ever be, including the Arecibo telescope. It's got to be bigger than that. And so with these three dishes, we are simulating a telescope with a diameter of about a mile. So imagine a telescope with a diameter equal to the distance between these outer two most dishes. And that's the resolving power you get with an interferometer. It's much easier to pull it off with a radio instrument than it is with an optical instrument, but they are doing that with optical instruments as well nowadays. And finally, we wanted to take the 3-element interferometer, which is this set of telescopes right here, and we wanted to stretch it even further. And so this little 45-foot telescope was built and placed about 30 kilometers away from the observatory. And with it in place, and the 3 telescopes I just showed you, astronomers were able to discern the point source at the center of the galaxy, Sagittarius A star. So the first inkling of a black hole in the center of the Milky Way with this interferometer. So none of those telescopes are in use anymore because guess what? In 1980, a telescope called the Very Large Array was built. And it is 27 dishes that can span a 30-kilometer diameter. And so, you know, it supersedes our little prototype interferometer that we had here at Green Bank. but you can still see all the telescopes because we never tear anything down. We let it fall down naturally, but we don't tear things down very often, including this one. So I forgot about this slide, but it's almost like I predicted it with my last statement. So this beauty was called the 300-foot telescope, 300 feet in diameter. It was a transit telescope. So think back to the 1700s when people were building transit optical telescopes that were so big. The 300-foot is a transit telescope too. It can only rock north and south, and it has to utilize the Earth's rotation to, get you pointed to a different part of the sky. So that's what it looked like one day in November in 1988. And then the next day in November, it looked like this. And so those of you who are familiar with the recent tragedy of the large dish in Puerto Rico called the Arecibo telescope, recognize that us folks in Green Bank really knew their pain because this happened to us back in 1988. And there was no putting it back together again. Luckily, nobody was hurt. And same is true of the Arecibo. I guess we could call it a collapse. It wasn't exactly a collapse, but the Arecibo tragedy. So what caused it? What caused that collapse? Well, some journalists in the United States thought that we were getting too close to figuring out there were aliens out there. And so they zapped the telescope before we could find out for sure. But in fact, it's called metal fatigue. And if I go back just 2 slides here, I'll point out the part that broke first is right here where my cursor is. There's a plate right there. And a lot of important beams are bolted to that plate. And that plate suffered metal fatigue and cracked in two. And then these big important beams had no plates to latch onto, and it just dragged the whole telescope down. But it's all okay. It's okay because we got the opportunity to build the Green Bank telescope thanks to Senator Byrd, who put in an emergency appropriation. He was the senior senator in West Virginia at the time and chair of the Appropriations Committee. So we were darn lucky that if it was 300 foot was going to fall down, it fell down when it did. So he put in an emergency appropriation and we started to build a new telescope. So this telescope also took 10 years to build, but you've got to give us a little bit of credit because we also designed it at the same time as we started building it. The easy parts we got right straight to work on because we knew that the money just has less oomph as time goes on, as inflation kind of bites into it. And we completed it 10 years after we started. So I'm going to show you the construction of this telescope very, very quickly. We took a time-lapse photograph, not a time-lapse. We took one still photograph every day during the construction and knitted together some of those to show you what the telescope looks like under construction. So that part was easy. Those are just a bunch of triangles, the base to hold up the important part. And we're building the elevation gear right now, and now we're building a platform for the dish. The dish segments are going up, and then the arm is going to be built next. There it goes, and now we're putting the skin on the dish, and ta-da! That's 10 years right there, a little less than 10 years in the making. So here it is in its completed state. It is so large, and I'm going to show you a few slides to illustrate that to you. And the reason why it's so big is so that it can be sensitive. It's not really for resolution purposes. It's for sensitivity purposes. It's to be able to see farther and see fainter. So the entire dish rolls around on a circular track that you might be able to notice at the bottom. And then the dish structure and this arm tip in elevation. And that's how we get our full motion across. Are there any questions in the chat right now?
Yes, there's a couple. Let me go back here. The number of scopes and how many are operational there? the total number?
Mm-hmm. Gotcha. So I'm going to say 9 now instead of 8 like I usually do. And I am going to say 5 of the 9 are operational. I have to count them in my head. It's been so long since I worked there. I mean, I've been at home for a year. But we have a new instrument that I'll show you. And then we're getting ready to build another one I'm so excited about. So I'll tell you about that too. Yeah, but the 3 85-foot telescopes are no longer operational, and the little outrigger telescope that that was used with it is no longer operational. I still count the 140-foot as an operational telescope because it's ready to go. We just completed one project with it, and we have no doubt that somebody else will come along and want to use that telescope, and we'll rent it out to them.
Okay, someone's asking about, do the radio telescopes do astroseismology? I never heard of that.
We participate in sort of acoustic studies of the cosmic microwave background. and we do watch things called neutron stars undergo starquakes. If anybody if you want to elaborate more on what you mean by astroseismology, not for planets and things like that.
Excuse me, I can say something about that.
Okay.
Helioseismology is the study of the natural modes of vibration of the sun. Now, with the brighter stars, that can be done, but I understand it's only done in the optical, not on the radio.
I think so, yeah. But I think there are corollaries to that kind of thing applied to larger scales. But I don't know very much about it. I mean, larger spatial scales, not like stellar scales, but more like cosmic scales. But yeah, I don't think we do helioseismology, but you know, Google me and prove me wrong. Not me, Google helioseismology and see if we do any of that. Okay. Anything else?
Yeah, why build such big telescopes when we can make a collection of smaller ones instead?
That is a great question. And it is because the only thing we have to change is right up here in this little box in order to have a completely new capability. We had a collection of smaller ones that still, you know, made up the same aperture here. We'd have to have whatever that N is. N equals the number of receivers and so forth. So the idea to have one big single dish is number one, to get large scale structure. We can't get fine structure, but if you use this big dish in combination with a collection of little dishes, you get the resolution of the little dishes all linked together, and you fill in the gaps with a telescope like this. But one of the main reasons is to be versatile, because we only have to change the lens, so to speak, at the focal point in order to have a new capability. So those two reasons, I think, are probably why.
Okay, and how are you going to manage metal fatigue in this telescope?
Yeah. So the first thing that we do is inspect the telescope a lot, and we really didn't back in the 300-foot days until we did postmortem. That's how we found out what broke first. And so we hire an external team to come in, and they use ultrasound and all kinds of other techniques, and they rappel underneath the dish and analyze these joints. And that happens every 3 years. So it's a part of our summer kind of shutdown that we do. And the other thing that I'll say is different about this telescope is that all those joints that you see there, every place where beams come together, those are welded. They're not bolted. So we don't have the same sort of flexion at the joints that we did with the 300-foot telescope. So we have these welds and we inspect the heck out of the welds is what we do. And if we see a problem, you can mitigate the problem if you do it before the telescope falls down. I hope so far you can anyway. All right, so a couple of slides to show you. Yeah, go ahead, you can ask.
No, we're caught up now.
Cool. All right, so I'm going to show you a picture of a portion of the dish. And during a maintenance day, and there are a lot of them in the summertime, that's how some people get to take a tour on the telescope in the summer, because we do a lot of summer maintenance. Sometimes it's required that one of our mechanics or a telescope operator needs to go out on the dish to do something, and you're seeing one of our telescope operators on the dish there. So I'm going to back that up a little bit, and there he is still, a little bit more of the dish showing, and there he is again. So if you're up above the dish looking down, that's about the size of a human being compared to this 2.3 acre surface. If you picked up the dish and plunked it on the mall next to the Washington Monument there, it would look like that. That's how big the GBT is compared to the Washington Monument. And then for the young at heart, I'll just put a couple of other references there. House, cows, barn, baseball diamond, no problem on the dish. So it is really, really massive. And again, that's for sensitivity purposes, to be sensitive and to be versatile. So if I were to be able to take you up, so if you were to come take a tour on the telescope, we would flatten the dish out because we wouldn't want you to have to climb up this really steep area here. But this is a walkway. So you take an elevator up to this level, and then this is a walkway that takes you to the elbow of the arm, and then there is an elevator that'll take you up to the receiver room. So this is the focal area, this whole thing. So here's a picture of it a little bit more zoomed in. So the elevator will drop you off right here. There's a door. You can go into a fairly large size room, and that's where all of the receivers that are designed and built and maintained by the staff at the observatory are placed. So you can probably sense the way the optics work here. Those of you that do observational astronomy, this is a Gregorian subreflector. So we're passing by the focal point, hitting the subreflector, and then refocusing into the appropriate receiver down below for the most part. You see this thing right here? This is a boom, and the boom can be swung up into the prime focus position. And our lowest frequency receivers go there. If you want to observe the universe at a frequency of 300 megahertz, then you're going to use our prime focus receiver that'll be in this boom, and we'll swing it out for you to use it at the prime focus. So this is what the receiver room looks like on the inside. So these are receivers hanging down from the ceiling. That's one of them. Here's another. Everywhere you see a hole, that's where another receiver is hanging down from the ceiling, and it actually protrudes through the ceiling, into the open air. So these little covers that you see, these little covers that you see on the roof of the receiver room are attached to different receivers. And each receiver is optimized for a certain frequency or wavelength range. It's like putting a color wheel, in front of your eyepiece. So we're interested in different wavelength ranges or frequencies depending upon what the astronomer is interested in, what they want to study. And just for, a little bit more for scale, this is a person standing on one of the trucks. So we have 16 wheels that roll this baby around on a circular track. And each wheel has to hold up about 1 million pounds of weight because the whole telescope weighs about 17 million pounds. This just shows you the way the telescope tips. This was still during the construction phase. Very old animated GIF here, but you get the idea. And then this is a picture of the telescope rotating in azimuth. So one of the things that we do on our tours at StarQuest, because you're special, is we take you into the GBT control room. Right now, while we're in COVID, nobody except for telescope operators are allowed in the control room. This is probably the best guarded room at the whole observatory. And that's because we don't have another place to really, control the telescopes from. I mean, we can, but it's not as good as this. And so we don't want to infect this room with COVID and have to boot the operator out into a less advantageous location for controlling the telescope. So this is a telescope operator, Amanda. She's no longer a telescope operator. She now works in the Education and Public Outreach Division, but she is in charge of not only the Green Bank telescope, but any other operational telescope on site. There are a set of screens for her to pay attention to that go with each telescope. And not only does she have to pay attention to the observers who are using the telescope, she has to pay attention to the safety of each telescope. If one of the systems goes down, she's got to be able to troubleshoot that or call in the relevant engineer or computer programmer or somebody to fix it. So that's the telescope control room. And it is also a Faraday cage. It's a shielded room because all of these computers generate radio frequency interference. And we want to keep that radio frequency interference from leaking out for the telescope to see. So it is a copper clad room, and there's a microwave oven in there that's also inside of its own Faraday cage, inside of this big room size Faraday cage. And there's a picture of, the GBT at the end of the rainbow right there, as it should be.
There's a question on the scopes are used for the Deep Space Network from like the Apollo era or current. Like, did I read or hear that it was used to contact someone with the Perseverance rover?
Yeah. We do. We provide backup. NASA is fabulous, but they are so thorough and they like to have backup. And the GBT is big enough to actually receive and detect the very faint signal from the rover, the robot, as it's going through entry, descent, and landing and chirping back at the orbiter that orbits Mars. And so GBT was there just as backup in case signal was lost in the normal NASA chain. And we've done that several times. And we also participate with Goldstone on radar types of studies too. So asteroid research and things like that. We participate with the Goldstone telescope. Any mentioned use for Deep Space Network? Well, yeah, I don't know whether we did the old stuff, Mercury, Gemini, Apollo. I don't think we did. I think the dish down there in Australia beat us out for a little bit of that, if you've ever seen the movie The Dish. Okay, I'm going to share screen again and I'll take questions along the way. Yeah, and just keep them coming, you guys. That's awesome. Okay, here we go. Okay. All right. Where are we? Oh, there we go. Okay, so now let's take a look at the radio universe. That's what we're all here for. We love the sky, we love the cosmos, and so the radio cosmos is pretty fascinating as well. And we're going to start out with a really crappy picture of the night sky here. If if I can make it happen. I've lost my ability. There it is. My ability to advance these things. So that's a terrible picture, but it's about the kind of picture I would take if I tried to take an image of the night sky. I'm not very good at it, but I use it to just illustrate that. You know, when you use your eyes to look at the night sky, you see some things out there, and you can differentiate between point-like objects like stars and nebula, like that blob of pink gas you see up there, and then the Milky Way itself, the large galactic plane running through there. So you can differentiate different types of objects just about with the naked eye, and certainly with a pair of binoculars. So if you had eyes that could see radio waves instead of, you know, the normal visible light sky, what would the sky look like to your eyes? And it would look kind of like this. So this is radio data superimposed over you know, a photo of the Green Bank Valley. And this radio image was made by scanning the 300-foot back and forth through the sky and measuring point by point whether radio waves were present and how strong they were. And so the brighter the dot, the stronger the signal that we received. And big things that you see on this view of the sky are big things that you see on this view of the sky. Maybe they're close, or maybe they're big. But this is what the radio sky looks like if you had eyesight similar to your vision, only in the radio part of the spectrum. Yeah. So just as an aside, your eyeballs, yeah, go ahead. Mm-hmm.
I suppose this is for some band of frequency, and it would look different at a considerably different band.
It would. Certain things would get brighter and certain things would get dimmer, for sure. But many objects in the radio sky are broadband emitters, and so you would see some signal from them, whether you're observing at low frequencies or higher frequencies. This data was collected at 1400 megahertz. So 21 centimeters wavelength. And it was collected with the 300-foot. And the 300-foot telescope was collecting this data when it fell down. So this was some of the last science that came out of a 300-foot telescope. So in this image, you do see some dots, things that kind of look star-like, point sources of brightness. And this is radio brightness. This is not visible light. These are sources of radio waves. And then you see some extended sources as well. So it doesn't look all that different from, you know, your view of the sky with your eyes if you look out at night and look up at the sky. The fact that the sky is not black is for real. And that's because everywhere you look with a radio telescope, there's some signal there. And that signal is the cosmic microwave background. So we don't ever get a completely black sky, although it would be black to our eyes. It would be more or less black. So what are these things? So, you know, in the 1960s, when the observatory was brand new, people really didn't know what all these things were or why they saw these bright sources of radio waves. They didn't know whether they were stars or just what the heck were they. So let's take our little tour. And this is just a set of pictures that I like, because a set of images that I like because it kind of shows you the contrast between all the different wavelengths of astronomy and why it is that astronomers want to do radio astronomy and ultraviolet astronomy and X-ray astronomy and everything else. If you look at the image of the sun, which is the bottom row of images, you might notice sort of a contrasting but similar set of images between the visible image and the radio image. And if you look at the set of images of Saturn, you'll think, well, that radio image looks pretty weird. So astronomers like to see it all. And I really Saturn, because you can see this enhanced brightness at the poles here in the UV. So I'm going to step you through. Yeah, go ahead.
I'll let you know it's 8:32, okay?
Gotcha. So I'm going to step you really quickly on how we make radio waves in the universe. And one way is with hot gas. So this is supposed to illustrate an atom to you with a proton being red and an electron being green. And essentially my bottom line for this next series of slides is if you can accelerate a charged particle like an electron, you can generate radio waves. And in this case, the green electron is being accelerated as it passes by the proton. So this is a hot ionized gas. And a lot of things in the radio universe emit due to this mechanism. And I'm going to show you this planetarium view of the Orion constellation region. I want you to pay attention to what you see here versus what you see in the radio image. So that's the radio image. And that's, you know, a representation of what you'd see with your eyes. So I want you to notice there are no stars in this image, okay? So stars are not a main source of radio astronomy science, but nebulae are. Ionized gas being ionized by new stars can result in bright radio objects. And the Orion Nebula is down here. This is the Rosette Nebula over here. And this is Barnard's Loop. Is that what that's called? I think. And then, you know, there's just some Milky Way going on here as well. So hot gas, ionized gas, nebulae are sources of radio energy, but stars not so much. And that's because even though a star is hot gas, it is a small, tiny, point-like object of hot gas dominated by its temperature rather than this free-flowing electrons being accelerated all over the place. And here is the Omega Nebula in 3 bands: radio, infrared, and optical. So this month, I think it's the 25th of this month, marks the 70th anniversary of the discovery of this phenomenon. This is the hydrogen atom, and the electron is undergoing a spin flip transition, as we call it, from up to down. And when that happens, it generates a signal at a very specific wavelength or frequency, and that's what we call a spectral line. And the discovery of neutral hydrogen, the neutral hydrogen line, was made 70 years ago this month. So here's an image of a galaxy, and this is a negative image, as you know. And here is data collected on the same galaxy with a radio telescope, tuning our radio telescope to the frequency of hydrogen. So a 21 centimeter spectral line corresponds to a frequency of 1,420.4 megahertz. And you can see that while close, the signal that we're picking up is not at that frequency. It's at a lower frequency of about 1,417 and change in megahertz. And that's because this galaxy is receding from us due to the expansion of the universe at a velocity of about 600 kilometers per second. And so that has redshifted the line to a lower frequency. And very quickly with a radio telescope, you can survey lots of galaxies and get lots of redshifts and start to build up a large scale picture of the universe and what's going on in it pretty quickly. So it's not a pretty image, but it is really valuable data. And then finally, if you get electrons trapped in magnetic fields, radio waves can be produced as well. And an electron is now the red ball, and the magnetic field is green. And you can see that the electron is spiraling around the magnetic field lines. So here's some examples of this kind of emission mechanism. There's Jupiter in the optical, and this is a radio image of Jupiter. And here's a sort of a radio image of Jupiter superimposed on an outline of Jupiter. And you can see that the magnetic fields of Jupiter are the cause of the bright radio emission here. So trapped charged particles in Jupiter's magnetic field give rise to these 2 ears of radio energy outside of the planet. There's the sun, and here's a radio image of the sun. And this is during the height of a sunspot maximum, and you can see bright spots of radio emission from above the location of sunspots where particles are interacting with the sun's protruding magnetic fields. Going out further in the Milky Way, we have this beautiful picture. This is a Hubble Space Telescope image. It's the best you can get with an optical telescope, or at least it was at the time it was made. And this is the radio image of this object. This is the brightest radio object in the sky except for the sun, although it's getting dimmer over time. So this should remind you of an explosion, like a still photograph of an explosion, and indeed it is. It's a supernova remnant, and charged particles are interacting with the remnant magnetic field from the star itself. So this is a star that went supernova long ago, and this expanding shell of gas is very bright to a radio telescope. Now, what might be left behind in a supernova remnant is the corpse of that star that had continued to collapse during the supernova event into a very, very dense core. And we call these things neutron stars. And they can be detected by radio telescopes if they're aligned such that we can see these beams of energy aiming our way. And so those two blue cones are accelerated charged particles that are being accelerated out of the magnetic poles of this stellar corpse, this neutron star. This is a big, big source of research at the Green Bank telescope and many other telescopes as well. And lastly, I'm going to take you out into the extragalactic universe now. We're going to leave the Milky Way behind, and we see a lot of these things. This was made with the Very Large Array Telescope, showing you detail we'd never be able to see with the GBT. And you can see here a bright source of rays in the center, and then some jets coming out, and some bright blobs of material that we call lobes. And they're very bright to a radio telescope. So this is a radio image again, a false color image. So trying to figure out what those are, we really need to work with optical astronomers. And this is an old superimposed image of another one of these things superimposed on an optical image. And the optical image shows, coincident with the bright spot that we saw at the center, an elliptical galaxy. And so as you look out across the radio universe, these shell-like things that you see here are probably supernova remnants. This linear blob down here at the bottom is a nebula. So you're looking at hot gas with ionized, that's ionized. And then all those other tiny little dots that you see on that image are distant galaxies with black holes in their centers. And we just can't resolve the jets with the 300-foot telescope that made this data. So some of them are quasars, and that's just radio galaxies where the jets are pointing at us, and so we can't see them anyway. And some of them are just, radio galaxies that we can't resolve the jets because we don't have the angular resolution here. So every single dot that you see, whether it's tiny and dim or bright, is a galaxy in the distant universe with a supermassive black hole in its center. And so the types of things that we study with our radio telescopes are these sorts of things where accelerating electrons generate the signals that we can pick up. Okay, so I'm going to stop sharing right now and see what questions there may be. And then at the end, I'll take you quickly to the 20-meter telescope. So do you have any questions about any of that, or just anything related to radio astronomy or the Green Bank Observatory at all? You're welcome to unmute.
There's a couple in the chat, if you can open that.
Yeah. Right, that galaxy, that's right. NGC 628. Do radio images use false color? Absolutely. So I'm so glad that you all use CCDs now, because it equates better to what we do than before when you use your eye. And so you are generating a grid, And all these little pixels in the grid are recording how much signal you're picking up. So all of your images are just a matrix of the sky with numbers associated with each pixel, right? It's brighter over here, so there's a bigger number associated with that. And it's the same for us. So radio images are merely a matrix of brightness versus position in the sky. And astronomers love the flame palette, and they like rainbow, and they like these things. And so they will color code those images. Now, if you do a 3-color image, so to speak, you would pick a color for the radio image and then a color for 2 other wavelengths and superimpose them to give you the sense of a true color image, but they're all false color images. Representational color, we should say. All right. What are your sources of funding? Right. So NSF funding is at about 60%. Breakthrough Listen is a big project we're doing with the GBT, and this is a couple of $1 million a year to use a portion of the Green Bank telescope to search for extraterrestrial intelligence. And we are looking for technosignatures. That's the fancy term for what they give to radio signals that are being generated by other civilizations. And so it's the most massive SETI project ever undertaken. And we have this going on for about 5 more years to provide that funding. And then another potential source of funding might be to up our radar game somewhat. We just published a very beautiful image of a little slice of the moon where I can't remember which Apollo it was, but there's and that was using the GBT to transmit and using the very long baseline array to pick up the signals. And with the VLBA picking up the signals, the resolution of the resulting radar images was pretty fantastic. So we may have a role to play there and may receive some funding from an outside of NSF to build that capability up slightly. And then we get little chunks of money from various projects like monitoring that Russian radio telescope for all those years. So we just kind of cobble it together. Has the loss of Arecibo pressure on time for Green Bank Observatory? Yeah. Yes, David, it is going to put more pressure in the coming months, particularly for a consortium of astronomers known as NanoGrav. And NanoGrav is using large radio telescopes like GBT and Arecibo to time very precisely the arrival time of pulses from pulsars. And they do this for years, and they have such an accurate model that they can predict when, you know, 1 million pulses later, exactly when it's going to arrive here on Earth. And using all of this timing data from pulsars all over the sky, all over the galaxy, they can detect very, very long wave gravitational waves. So they've just released a whole new data set. Arecibo was a big part of it, and GBT was as well, where they have tantalizing evidence of a first detection of this stochastic gravitational wave background. So the loss of Arecibo is going to be very keenly felt by them. You know, the GBT has a multitude of observers, and so it is going to increase the observing pressure for sure. Howard says, are you no longer affiliated with the NRAO? That is correct. So back in 2012, I want to say, an external commission took a look at all of the facilities that the National Science Foundation funds, all the astronomical facilities, and determined that in order to build things like the Rubin Observatory, the Large Synaptic Survey Telescope that's being built in Chile right now, that in order to be able to do that and fulfill astronomers' wishes for their priorities, that they were going to have to uncommission, descope some existing observatories, including some of the 4-meter class telescopes that the National Optical Astronomy Observatory operates, and the GBT. But NSF has been very helpful in helping us look for new partners And they have given us quite a commitment to fund us at the level they're funding us now over the next 5 years. And that's typical, that you get a contract for 5 years and then you have to re-up it. So we're in better shape, now than we were, say, in the mid 20 teens, trying to figure out how to keep the observatory working. So the kinds of equipment that you shouldn't use while you're visiting the observatory for StarQuest are just digital things. You're going to be you would be in a field that is, you're given special dispensation to be down there. We know your telescopes have motors and computers and things like that. And so we allow that for the 3 days. But if you advance down the site, if you want to take a hike down the site or anything like that, we want you to leave all your digital stuff turned off. Cell phone cameras off. Fitbits, leave them in the car. All that kind of things, because you'll be walking past the telescopes and getting close enough to really generate some RFI. The lowest latitude or altitude is about 5 degrees above the horizon. So we can actually see, and we can see, all the way across the top. So we see 85% of the celestial sphere with the GBT, of the entire celestial sphere. So it can observe 85% of the celestial sphere. I know. That's right. Okay, so let me share my screen just for a few minutes, because your league, let me start there. I'll start with this because this is cool. I'm just proud of you guys, you folks. So I went to your website, and of course I knew about this already, but the Astronomical League has a radio astronomy observing program, and the medals are so cute that you can earn if you do the program. And it allows you to build your own radio telescope and do that if you want. And you can also use the facilities at the Green Bank Observatory. And now the 40-foot's not available while we're all socially distanced from the observatory, but the 20-meter is. And the 20-meter telescope, I showed it to you on the tour, has an interface to it that was built by a group of astronomers and software geniuses at the University of North Carolina. This interface is called the Skynet Robotic Telescope Network. Joel knows all about it because he has been involved with some of our educational programming in the past. And so Astro League has that's what we call it, astro.league. You have a login to the Skynet Robotic Telescope Network. And if you click on radio observing.
And we're not seeing your screen.
Oh, okay. Thank you. Always forget to hit the little share button there. All right. They're good. So I'll take you home here. So this is skynet.unc.edu. And I'm logged in as me.
We're seeing your PowerPoint still.
You are?
Yeah, we're seeing your editor's, your presenter screen.
Gotcha. Now what do you see?
We see the Zoom screen, nothing right now.
Ugh. Okay.
It's got to pick that right window.
I've been doing this for a year. You'd think I'd know how to do it by now. All right, here it is, right here. Skynet. Yes? No,
yep.
You still don't see it. Do you see it?
We're okay. Good now. Yep.
Okay, cool.
Skynet.
All right. So, if you go to my observatory, so you have to log in, and your login as an astronomical league person is astro.league. And I'll give Don the password, and he can give it out to you in case there's any Zoom bombers out there. Don't want any Zoom bombers to have the password, but I'll hand it out to you, and then you can pass it around if you want. And I put some telescope time in there.
Yep, right? That works great.
Okay, and so you have to click on radio observing because I did not give you any optical telescope time, but there you can talk to Dan Reichert at UNC if you want in on that. You'll have to pay for it. But the radio telescope is right here. And all you'll do is say, add new observation. And you'll go on through and, collect some data. So what you see when you click add new observation is a view of the sky over the 20-meter telescope right now. And these are some radio objects that are up. You can also toggle the Messier catalog if you want to see if those give off radio waves. You can click on a star, but I've already told you not to do that because stars are not good sources of radio science. But let's just say we wanted to observe the Crab Nebula. Well, we could click on it, or you could write in something in the target lookup here if you wanted to. So once you clicked on the Crab Nebula, it populates the right ascension and the declination for you. It gives the observation a name, and you might put in your initials so that you can find it later. And then down at the very bottom of the screen, it just shows you when your target's going to be up. So the Crab Nebula is up right now, and over the next 3 hours or so, it's going to sink below 20 degrees elevation, and that's just sort of a nominal cutoff point, but you can lower that if you want, and then you won't be able to observe it for a while. So it's just showing you when you're likely to collect some data. So we'll save and continue there, and then you've got some choices to make, and we have a little observing blurb for you to help you step through that. But if I pick high resolution mode, that's going to give me the ability to see any spectral lines that might be there. But I do low resolution mode quite a bit as well. I'm going to save and continue. And then I'm going to pick a little telescope motion called Daisy Scan. In radio astronomy, you very rarely want to track. You'll make a mistake if you use some of your observing time to track an object, because I don't have a CCD with multiple pixels. The 20 meter is a 1 pixel telescope. And so tracking just doesn't get you anywhere. If you do a daisy scan, you're moving on and off your source. You're moving away from it and on it. And that way you can see the contrast. So I'll just pick a radius here of 180 arc minutes, 4 petals, and maybe I'll do 120 seconds. And if I save and continue, then it just shows me a list of things that I decided on. So I want to click submit. The reason why I'm doing this right now is because I hope the telescope's working, and I'm going to show you it working in real time. So now my observation shows up and it says it's ready. That doesn't mean it's doing it. It means that we're in a ready state, and the telescope will execute the observation when it gets to it. So there's a queue. Other people might be using the telescope, who knows? But I'm going to go to telescope sites and go to Green Bank. Oops, sorry. And then, all right. And then I'm going to click on, oh, look there, it is me. I'm going to click on this Green Bank 20 link here. I'm going to show you what's going on. So this blue bullseye is the telescope moving. And it's going to move over beside the crab. I'll zoom in a little bit for you. And now the telescope is sitting still beside the Crab Nebula. And what it's going to do is it's doing a little reorienting of itself because I asked it to do some spectral line observing. And then we're going to watch the telescope move across the object. So I set a daisy scan with 4 petals. So pretty soon all this, the orange and the blue line will sort itself out, hopefully. And you'll be able to see the telescope moving. Here we go. That looks better. Okay. So that's all just meaningless material going by. This is supposed to be a running look at data as it happens. And we'll see. Okay, it looks like a little calibration occurred. All right, So now the bullseye is in motion. Do you see that? So it's just sweeping underneath the Crab Nebula. And you can see a little lump right here. When it passed under the Crab Nebula, this will scale itself in just a minute. And now the telescope's going to loop around and do it again. All right, here comes pass number 2. There we go. So now we have a calibration signal on the left. That's pass number 1, this sort of hump that you see here. Pass number 2 is also another hump, and it's going to give you 2 more because we said we wanted 4 petals on this particular observation. So this is just a measure of signal versus time that's going by on our little strip chart recorder. How much signal? So how bright is our signal versus time going by? It's not telling you anything else other than that. Any questions as we look at this happen? And then I'll show you what your data looks like. And our last pass through here.
Question.
Yep.
What frequency is it observing?
Yeah, so the frequency range of this receiver goes from 1,300 megahertz to 1,800 megahertz. And we left a filter in place. We call it the H1 filter. And so it's only 15 megahertz wide. So we've thrown away most of that range, and we're only looking at a 15 megahertz wide chunk of the band centered around 1420 megahertz. All right, cool. So that was its last pass, and that's a final little calibration signal, a man-made calibration signal. Is how we do it in the radio world. And so if I go back to my observatory and radio observing, let's see. Oh, look, my observation is complete. So now you can click on the ID and click again. And I'll send, and there you go. So on the left, you see exactly what we did. And then on the right here, you see, instead of time running along the bottom, you see frequency, observing frequency along the bottom. And lo and behold, in the direction of the Crab Nebula, we do see a signal at around 1420 megahertz, which is the signal of neutral hydrogen. So that's just in the general vicinity of the Crab Nebula is what we're seeing that there. And in a minute or two, oh good, yeah. In a minute or two, we can see some more data show up too. So this is the pattern we made in the sky relative to the right ascension and declination. This little green circle is showing you the resolution of the telescope, the resolving power of the telescope. So you can see it's just a little less than a degree. And these are weird images that do not approximate reality. Really, I think we went pretty fast. So this is the software trying to interpolate between my daisy petals what we are looking at here, and that's pretty cool looking, but that's not really what I would expect the Crab Nebula to look like. But this was just an example of an observing mode where you can get a spectral line, you can get a measure of, just how bright the Crab Nebula is all at once. And you could even get a crazy looking image. My advice would be use 8 petals instead of 4 and go slower. So there's a piece of data. So this and more is available to you if you would like to explore radio observing for yourself. So who's ready? Who's ready to be a radio astronomer? Come on, let me see some thumbs up or a hand wave. Absolutely.
Thank you very much, Joanne.
All right. Well, that's what I have for you. Happy to answer more questions or chat if anybody has other things you want to chat about.
So what was that? You said
League.
League. Okay.
Yeah. Yep. So you would go to skynet.unc.edu and then go to sign in with astro.league. And then there'll be a password to go with that I'll give Don. So reach out to Don and he'll.
You can always listen to Sue's narrative again because the entire presentation is on YouTube. It's the link that was in the email that I sent out with the invitation. You can follow that. And you also see all the meetings that the astronomy club I'm in has been having all year. So, but yeah, the meeting will be there. You can walk you through the directions again.
All right. It was great to see you guys.
That was great. Thank you so much.
You are welcome.
Thank you very, very much. I learned an awful lot.
You did your usual excellent self, Sue Ann.
Thanks.
And I'm looking forward to seeing you this summer, I hope.
I know. Fingers crossed.
We hope so too.
Thanks, Sue Ann, for fitting this in with all your extremely busy activities going on right about now.
It's been a tough couple of weeks.
Thank you, Sue Ann.
You're welcome.
Great to see you again.
In April.
Okay.
See you in April.
All right. See you then.
We peaked out at 88 people. I've never seen that many on a presentation before, ever.
Cool. Well, I'll send you an email right now, Dawn, with that password, just in case somebody hits you up. Okay.
Okay, great.
All righty. Have a good night.
You too.
Thanks.
Thank you.
Bye.
All right, so Don, what's our next presentation going to be?
That's a good question. Well, I wish we had this going